Howdy, hey, Spaceman Josh here, and today we're talking about the geometry of space-time. So, with space-time, it's encompassed under Einstein's theory of general relativity, and so the core of general relativity, which also happens to be sort of an acceptable alternative name, is geometrodynamics. And so the presence of matter and energy sort of alters space-time geometry, and that altered geometry influences the motion of an object. And that relationship comes from one of the fundamental concepts of general relativity, which is the equivalence principle. When the equivalence principle is the assumption that the inertial mass and the gravitational mass are the same property. They represent the same thing. And a good way to sort of think about this is if you're, say you're in a spacesuit up orbiting the Earth and you're facing the Earth, and you have yourself a bag of M&Ms, and you decide you want to open the bag of M&Ms and let all the M&Ms sort of scatter outward towards the Earth. And so, by chance, may have some of them that go just straight towards the Earth, but a lot of them will not. They'll have some other non-straight horizontal trajectory. And what will end up happening is you can sort of see them all sort of start to turn and start going directly towards the Earth, towards a sort of a perpendicular to the sort of the surface of the sphere of the Earth. And if the Earth if the M&Ms were able to go through the Earth, what would actually end up happening is the M&Ms would go through until they hit towards where the center of the Earth is at, and all the M&Ms would collide together in that same spot. And so the trajectory that each individual M&M took shows the complex nature of gravity and how it affects the different things. And the reason that's important is because gravity is actually the geometry of space-time. And that's cool and all, but we also can't be forgetting time. There's space-time. We have time as well as the space part. And so gravity is the geometry of space-time, but we can't forget about the time. Gets really hard because and so you can sort of think of if I've seen this experiment, you can sort of get a better idea. But I'm also going to describe it where you have, say, like a trampoline or some really sort of a bendable silk or some sort of fabric. And you have this in the middle, you place like a bowling ball or some heavy large object. It would represent a planet, a star, a black hole, whatever you want it to represent, as a large massive object. And you have some other objects, normally spherical objects, you'd send around the trampoline or the fabric, whatever you have, and so the objects want to go in a straight line, but because the bowling ball in the center is pulling down the fabric of the trampoline, they end up being curved and taking a path around the object. The small, a lot of people use marbles. The small marbles want to go in a straight line, but they can't because of the curvature of the trampoline. And it's a simple enough example to get the idea of what happens with space-time, but it's just not enough. Space-time is in 4 dimensions, and the sort of trampoline demo, really the most you can give it is 3 dimensions. And so having to look at space-time in 4 dimensions is really, really hard to visualize. Even when you try to do it with some mathematically, I have this sort of picture here that I have of what's called a light cone. And so if an object was at the origin of of all these axes, so it's right in the origin 0, 0, 0, and it was traveling, there's only nothing can travel faster than the speed of light. And so there's sort of this area the area in space-time that it can travel, that sort of all the possible places it could end up traveling if it was traveling at some speed. Now, I want to explain this graph a little bit. I have sort of the x-axis over here and a z-axis over here. Those are just space dimensions. You can't really add a y because here we have I have written here ct. C represents the speed of light, and t is just time. It's sort of a way to graph time in sort of a place in sort of a displacement sort of way. and so that's what we just take time and we times it by the speed of light. That way and we have seconds and meters per second, so you end up with meters just like in x or z. It's a way to be able to sort of visualize that. And the most we can do with this is 2 space dimensions and then the time dimension. Unfortunately, there's no way really drawing 4 dimensions on a 2-dimensional surface. But the 2 cones you see on coming away from the origin is the light cone. The only one that really is important for us in terms of the space-time and geometrodynamics is the top one. This is where all the possible places it could go for an object traveling less than the speed of light. And so it's this idea that what's interesting with this idea of the light cone is with space-time. If you have an object, say you have the sun, and you have one of those M&Ms, it went off all in LA because you weren't aiming directly at the Earth. So now you have an M&M, and it's let's say it's next to the sun, it's orbiting really close to the sun. What ends up happening is because the sun is distorting the space-time around it, you end up the light cone actually moves, and so that changes the different possibilities that the M&M has to travel. Some places it could have gone, it can no longer go, as well as some other new possibilities it could go that now have sort of been affected by the mass of the sun being right there and distorting space-time. And this does seem really weird, and I know that I talk pretty fast, so if you want to sort of go back and sort of slow down the video a little bit so to get a better idea of what I'm trying to get at, or just you can also look it up online. There are a bunch of different places that try to talk about this and sort of explain this. Some of them a lot better than what I can do. But in the end, the math actually does work. There are a bunch of different equations in general relativity, and so some of these when you combine the results of those equations from the calculations, you actually see accurate and full predictions of the how an object is affected in space-time. And it's really interesting thing that the gravity is the gravity of affected by an object is actually represents the geometry of space-time. It's, for me at least, it's really super interesting, and it's really hard to just visualize, let alone from going from a light cone, visualizing just 2 space coordinates and then a time, to even thinking about what it sort of looks like in terms of imagining a sort of three space, sort of like a cube, and have an object in the middle, and how does lines represent how space-time is affected, and how there's some sort of distortions near where the mass is at. All these different things that make it really sort of interesting, but also super hard to sort of visualize. And that's one of the things about how a lot of people learn, especially a lot of scientists, including myself, that it's very easy to understand a concept when you can start to visualize it. That's a whole other side. That's a whole thing with math. You can either use the numbers to analytically analyze it, or geometrically analyze it with pictures. And for something that's really hard to visualize, it's an interesting concept, and we've sort of, I guess what I'm sort of trying to say with this is that it's nothing's disproven it, and so we have this thing that we have to accept as true, and we can't. It's for a lot of people learning, it's very difficult to sort of internalize how that affects everything, and that's all I really have to say about that. Thank you for listening to my rant. If you like these vlogs, or if you or just really my channel in general, please subscribe. If you want to, you can click the bell to turn on notifications, get notified exactly when I upload. And other than that, thank you for traveling with me. Spaceman Josh, out.